Hello everyone, welcome back to Physics 425. What we were working on last time was substituting in this wave function for the superfluid fraction of a sample of liquid helium-4 into the time-dependent Schrodinger equation. We did that, we did some manipulations, and then we ended up with a complex equation, complex meaning that it had real and imaginary parts. And what we did is we said, well, okay, the real parts of the left-hand side and the real parts of the right-hand side have to be equal to each other. And, oh, sorry about that. That led to this expression. We did some further manipulations, which we were able to, under some certain approximations, one of the approximations we made was that the superfluid density, rho s, is approximately constant. And so we threw out a spatial derivative of the superfluid density. And when we did that, we got this expression in the red box. This is an energy equation. So on the right-hand side, we have the chemical potential, which last time we interpreted as the potential energy per particle. And then the second term on the right-hand side is clearly a kinetic energy, 1/2 m times v squared. What we're going to do today is we're going to take this equation star and we're going to take the gradient of it. And if it's currently an energy expression, when you take the gradient of an energy, you get force. And so what we're going to do is convert equation star into a force equation, which will be an equation of motion for the superfluid. And so that's one of the things we'll do today. Before we do that, I want to start with looking at the imaginary part of Schrodinger's time-dependent equation. And so if we take the imaginary terms on the left-hand side and the right-hand side and force them to be equal to each other, this is the result that we get. And so we're going to try to do some manipulations of this expression, and what it's going to do is this will lead to something called the continuity equation for the superfluid. To see how that's done, let's just remind ourselves of a couple things before we start. So one is just to recall that what we did is we were going to choose the normalization of our wave function such that the amplitude squared was equal to the number density of superfluid helium atoms. And so it's the mass density divided by the mass. And so what that will mean is that if we have something like the mass times the square of the wave function, that's going to be the mass density of the superfluid. Of course, the other thing we know and that we've used multiple times is that the gradient of the phase of the wave function multiplied by some constants is the superfluid velocity. Okay, so let's see if we start with this equation for the imaginary terms. What we can first do is let's just divide out by one factor of h bar, and what we would get then is 1 over phi 0 d phi 0 dt is equal to minus h bar over 2m4, and then we have 2 times the gradient of phi 0 dotted with the gradient of the phase divided by phi 0 plus del squared of the phase. Okay, so what we're going to do is we're going to multiply both sides by 2m phi 0 squared. Okay, so when we do that, what we're going to end up with on the left-hand side is 2m, one factor of phi 0 cancels, and then we have d phi 0 dt. And then on the right-hand side, we're going to have minus h bar over m. So I'm going to cancel the factor of 1/2 with the 2, but I'm not going to cancel the m. I'm going to take that other factor of m inside. So we have 2, and there's the new factor of m. We cancel one factor of phi 0, and then we have the gradient of phi 0 dotted with the gradient of s. And then we have plus m4 phi 0 times del squared s and close bracket. Okay, so what we could do then is we can say, well, I could rewrite phi 0 d phi 0 phi 0 times d phi 0 dt as d by dt of phi 0 squared. So that's approximately right, but it would have a factor of 1/2 in front. So then that means that this whole thing is, we can use this 2 to cancel the factor of 1/2. We can take the m4 inside, and remember m4 times phi 0 squared is the mass density. And so what we really have then is that on the left-hand side, this is equivalent to d by dt of m4 phi 0 squared, which is just d rho s dt. Okay, let's see. Sorry, on the right-hand side, we have this m4. This should be a square because we multiplied by phi 0 squared. m4 times phi 0 squared is the superfluid density. And we can do something similar with this gradient of phi 0, something similar that we did with the time derivative. This is all equivalent to the gradient of m4 phi 0 squared. Sorry, I don't know why I put a square there. This is just a gradient. Okay, and so that's just equal to the gradient of rho s. So bringing all of this together, what we have is d rho s dt is equal to, let's see, minus the gradient of rho s. And then we have an h bar over m4, so we can dot that with h bar over m4 times the gradient of s. And then we have minus, we still have the minus h bar over m4, and then we have rho s times the gradient. So I'm going to write, del squared now as the divergence of the gradient of s. Okay, and so this is the del squared s. Okay, so this is Vs, and let's see, what do we have here? We can take the h bar over m4 inside the two derivatives, inside the divergence and the gradient. Actually, no, we don't want to do that. We want to write this as rho s times the divergence of h bar over m4 times the gradient of s, and that is equal to rho s times the divergence of the superfluid velocity. So finally, collecting everything together, we have d rho s dt is equal to minus the gradient of, there's a typo here, this is a rho s dotted with vs, and then we have minus rho s times the divergence of Vs. We can do one final thing, is we can simplify the right-hand side further if we write this as the divergence of rho s times Vs. And if you were to apply the product rule, then you would get the you'd get the gradient of rho s dotted with Vs plus rho s times the divergence of Vs. Okay, good. So this would be the product rule for the divergence you'd have to apply. Typically, this product of the mass density times the velocity is defined as Js. This is a mass flow rate per unit area. So the final version of this expression, which we got from the imaginary part of the time-dependent Schrodinger equation, is d rho s dt is equal to minus the divergence of Js. And this is known as the continuity equation. Continuity equation for the superfluid component in our two-fluid model. So just to interpret this, let's imagine we had some kind of spherical volume, and suppose that we had a positive divergence from the, let's say from the center of this volume, so that divergence of Js was greater than 0. So a positive divergence means that we would have flow out of this volume, so you would have some mass flow rate across the surface area of the sphere from the inside towards the outside. And so if that's happening, then it would be true that we'd be losing density inside of that sphere. The fluid would be flowing out, and so therefore the density would be decreasing, and so that's the reason for the minus sign in the continuity equation. And so at least that's consistent. Okay, good. So what I want to do is I want to return now to the real part of the Schrodinger equation, which we did some manipulation of last time. So let's go back to star, and so we'll just rewrite it. It was h bar ds dt is equal to minus mu plus 1/2 m4 vs squared. Once again, let's just remind ourselves of a couple of identities that will be useful before we get started. We'll make use of the following. A dot b is a scalar, and so we can take the gradient of the scalar. So if we do that, the gradient of a dot b, that is equivalent to, there's 4 terms. It's a dot del b plus b dot del a plus a cross del cross b plus b cross del cross a. Okay. And so the other thing we'll just remind ourselves of is that if you take the curl of a gradient, you get 0. Okay, so let's take the gradient of this equation star. Okay, so h bar, and then the order of derivative doesn't matter, so let's do d by dt of the gradient of s. We can see already that that's going to be useful because we know that the gradient of s is related to the superfluid velocity. And then on the right-hand side, we would have minus the gradient of mu plus 1/2 m4 vs dot vs. And so you could already see where this first identity is going to be important because we're going to have to take the gradient of vs dotted with vs. That's kind of nice actually, because then instead of having an a and a b, we just have the same vector, which simplifies that first identity a little bit. Okay, so let's just remind ourselves that the gradient of s could be written as m over h bar times vs. And so if we do that, what we have is, well, when we sub that in, the h bars are going to cancel, and we'll just have an m4 d by dt of vs. And then on the right-hand side, so we'll have minus the gradient of the chemical potential. Nothing we can do there. But then we'll have minus 1/2 m4, the gradient of vs dot vs. Okay, so if a is equal to b, then in this first identity, these first two terms become identical, and the second two terms become identical. And so this is equivalent to 2 vs dotted with del acting on vs plus 2 vs crossed with del cross vs. Okay, but del cross vs is equal to del cross, well, vs is what? It's h bar over m4 times the gradient of s. But we just said in identity 2 that if you take the curl of a gradient, you get 0. And so here we have the curl of the gradient of our phase, and so this is equal to 0 by the second identity. Okay? And so what does that mean? What's left over? We've got m4 dvs dt is equal to minus the gradient of the chemical potential minus, let's see, the 1/2 is going to cancel with the 2, so we're going to have m4, and we're going to have a vs dot del times vs. So we have vs dot del times vs. Okay, so rearranging some terms, dividing by m4, this could be written as dvs dt. Let's take the other vs term over to the other side, so the minus becomes a positive. We've divided by m4, so we get a plus vs dot del vs, and then that's equal to minus 1 over m4 times the gradient of mu. This I'll call equation number sign. And so what this turns out to be is, it's known as an Euler equation for an ideal fluid. An ideal fluid is one that has no viscosity, so it flows without any losses. So what we're going to do is we're going to try to interpret the left-hand side of this equation. It may be familiar, this may be something you've seen before, but what we're going to try to argue is that this left-hand side is like an overall acceleration. And so in order to kind of convince ourselves of that, what we'll have to do is really pay attention to the second term on the left-hand side of this equation. On the right-hand side, we have the chemical potential, which we interpreted as the potential energy per particle, and then we're taking the gradient of that. And so the gradient of a potential energy is minus the force, and so we have minus the gradient of mu, which is a force. If we divide by mass, then that is like an acceleration. So we have basically like a force is equal to an acceleration, or what we really have is A is equal to a force divided by m. So it's like a Newton's law for the fluid. And so this here is minus the gradient of potential energy. It's not really that important, but divided by mass. Okay, so this is like equation of motion for the fluid. Its equivalent to acceleration is force per unit mass. Okay, so let's think about this claim that the left-hand side is the acceleration. So in Cartesian coordinates, we could write down a general vector for the superfluid velocity as an x component and a y component and a z component. And so this superfluid velocity is going to depend on position. And then each of these components, the Vsx, the Vsy, the Vsz, could be time dependent as well. And so our velocity depends on these 4 coordinates, 3 spatial coordinates and 1 time coordinate. So if we were to take a derivative with respect to time, sometimes this is called the material derivative. You've probably seen it in several places before. One of the places that it comes up in is an advanced mechanics class. And so if we want to take this derivative, then we have to do chain rule properly. So for example, if we're just thinking of, I've written down just the x component. So we're just thinking of the x component. It depends on position and time, but each of the position coordinates x, y, and z has its own time dependence. And so by chain rule, we would have a partial derivative of this x component with respect to x times dx dt. And then the same for the y derivative and the z derivative. And then there's also the explicit time dependence. Okay, but this x dot is just Vs, the x component of Vs, and y dot is the y component, and z dot is the z component of the superfluid velocity. Okay, so let's just compare that to, let's compare to this thing that showed up in our derivation of our equation of motion for the superfluid. So let's see, we're going to have Vs dotted with the gradient, then acting on Vs. So Vs dotted with the gradient is the x component times an x derivative plus the y component of the velocity times the y derivative plus the z component of the velocity times the z derivative. And then that's going to be acting on the Vs vector, which is an x component, a y component, and a z component. And so if we focus just on the x component in the second bracket, what we would do, or what we would get after multiplication, is Vsx dVsx dx plus Vsy dVsx dy plus Vsz d by dz of Vsx. Okay, and then that would be all in the I-hat direction. And then we would have analogous terms for the j-hat and k-hat components. Okay, so this is Vsx dVsx dx. And so those are exactly the same. And then this is Vsy dVsx dy. And so that's exactly the same as this. And then finally we have Vsz dVsx dz. And that corresponds to that term. Okay, and so what we can do then is we can say that this collection of three terms could be more easily or more compactly expressed as the x component of Vs dot del acting on Vs. But remember, where this came from was just the so-called material derivative. It's a time derivative, and so it's evaluating how the x component of the supervelocity evolves with time. Okay, and so that means that therefore this dvs dt plus Vs dot del acting on Vs just describes how Vs evolves with time. And so that's just a long-winded way of saying that it describes the acceleration of the superfluid. Okay, and so let's just then rewrite this equation number star so we have it nearby. So it's exactly this derivative, which we said is the acceleration. And then it's equal to minus the gradient of a force divided by the mass. And so there's minus 1 over m4, and then it's the gradient of mu. And so let's just double check. Yeah. So this is just a rewriting of equation number sign, where now we've kind of tried to convince ourselves that in fact the left-hand side is an acceleration, minus the gradient of the chemical potential is a force, you divide by mass, and so that's equivalent to Newton's second law. So there's no dissipation in this equation number star, and so my claim is that this is somewhat analogous or like a mass falling in a gravitational potential energy. Wow, I should really say a gravitational field. Okay, so to see that, what we could do is we could start with a statement of conservation of energy. And so for us, how is this analogous to our analysis? Equation star that we started with from, which came from Schrodinger's time-dependent equation, was an expression of some kind of conservation of energy. And then what we did to get number sign is to take a gradient, a spatial derivative. So what we're going to do now is we're going to take a y derivative for, say, a mass falling in the y direction. So if we take a y derivative, sorry, no. I'm not going to take a y derivative. I'm going to take a time derivative. Okay, so sorry. Let me take a time derivative. So if I did that, what would happen? We would get an mv dv dt plus mg y dot, which would be v, and we have a constant, so the time derivative of constant is 0. So let's see, if we rearrange, we could say, and divide by m, we could divide by v as well. We get minus g is equal to dv dt, and so this is our acceleration term, and so that's analogous to the left-hand side of equation number sign. And then minus g is minus the gradient of a potential energy per unit mass. And so to see that, the gravitational potential energy is equal to mgy, and so this is here where if we take minus the spatial derivative of the potential energy, that would be equal to minus mg, and then you divide by mass, you get minus g. So in some ways, our equation of motion for the fluid is analogous to a mass falling in a gravitational field. If we were to include, say, air resistance, then our equation of motion for our falling mass would be modified. It would be modified with an additional loss term. So let's say we had a free body diagram. Here's the gravitational force, and maybe we have some drag force that's proportional to velocity. And so if we write down Newton's law, F equals ma, so F is the net force, and so let's say minus mg plus cv. And what we could do is we could divide by mass, and we would get, if we isolate minus g, that would be A, which is dv dt, and then minus c over m times v. And so now we have some of the same terms minus the gradient of the potential energy and the acceleration. So those two terms we had before, but now there's an additional term, and so this term represents dissipation. Some of the mechanical energy is converted into heat. So for comparison, if we were thinking about a fluid that flows not without dissipation but with some finite viscosity, then we would end up with the so-called Navier-Stokes equation for fluid flow. And for an incompressible fluid, this Navier-Stokes equation takes the form of dv dt plus v dot del acting on v. So this is the acceleration term. We have this term for our superfluid, and then it would be equal to minus the gradient of the potential divided by m, and so this is minus the gradient of the potential energy. And so we have that term also in our superfluid flow expression. In that case, the chemical potential plays the role of the potential energy. But what you have for a viscous fluid is a term that looks like this, and so this is a dissipation term. And this eta is the viscosity. And so what we were able to derive was something that's equivalent to the Navier-Stokes equation for fluid flow, which is a purely classical expression for the case where there's zero viscosity. And what's really neat about this is that we did this derivation starting from a wave function that was postulated to be valid to represent all of the particles inside the condensate, and we did a completely quantum mechanical calculation using the time-dependent Schrodinger's equation, and yet we recover the same kind of result that we would get for classical fluids. And so that's where I'm going to leave it for today. And next time, what I think we're going to try to do is to see if we can apply some of these results to look at a particular phenomenon that exists for superfluids. Okay, thank you very much, and we'll see you next time.